Hello everyone, and welcome to a video on Hardy-Weinberg principle, and we're going to be trying to making it as simple as possible. So the principle of Hardy-Weinberg states that the allelic frequencies and genotype frequencies are stable in a population over time. So let's just say we have an allele big A, so the dominant allele, and an allele small a, the recessive allele. The Hardy-Weinberg would state that the two alleles would be constant in a population over time, but they also state that the genotypes made from those alleles, so the big A, big A, big A, little a, and little a, are also constant as well. So let's just put that into a context. So cystic fibrosis is an autosomal recessive condition, so therefore the allele that would be carrying the cystic fibrosis gene would be the small a because it's recessive. So a Hardy-Weinberg population would mean that the frequency of the OK dominant allele and the cystic fibrosis recessive allele would remain the same, but the genotypes, big A, big A, big A, little a, little a, little a, would remain the same, i.e. the people that were carrying it would remain the same, and the frequency of people that had it would also remain the same over time. So the Hardy-Weinberg population only really applies when the population has specific characteristics. One of these characteristics is that the population is large. The other is that the mating is random and there's no selection. And then the other is that there's no immigration or emigration potentially bringing in new genes into the gene pool. There's no new mutations and there's no consanguinity, which means there's no incest. And only when you have sort of fulfilled these 5 main criteria can you say that a population is truly in Hardy-Weinberg equilibrium. And this is very, very rare, so it's more of a theoretical concept, but it's important to be able to calculate using this. So coming on to the equations now, there's 2 main equations we need to know. Let's have a look at the first one. So the first equation is P plus Q equals 1. And this equation is looking specifically at the frequency of alleles. So P is representing the frequency of the dominant allele, i.e. our big A. Q is representing the frequency of the recessive allele, i.e. our little a. Okay, so this is frequency of alleles. Let's just have a look at what that means when we're looking at genotypes. So the P, as I said, representing the dominant alleles, would be this aspect of the genotype, whereas the Q, the frequency of all of the recessive alleles, would be representing this aspect of the genotype. So there's a relationship with the genotype frequencies, but it's not the same as the genotype frequencies. The second equation to know is the p squared plus 2pq plus q squared equals 1. And this equation is representing the frequency of each genotype. So the p squared as a whole is the frequency of the homozygous dominant genotype, i.e. big A, big A. The 2pq is representing the frequency of the heterozygous genotype, i.e. the big A, little a. And then the q squared, as you probably guessed, is representing the frequency of the homozygous dominant genotype. Okay, so as you can see, this equation is specifically for the frequency of each genotype, not the alleles, the genotype. So just to make sure you've got that, the first equation, P plus Q equals 1, these are representing the alleles, the allelic frequencies, and then the P squared plus 2pq plus Q squared equals 1 is representing the genotype frequencies. So now we've got to be able to use these equations to answer some calculations, and a lot of the time these can appear quite challenging. Professors may overcomplicate them, but really, realistically, the best way to get through these calculations is with practice, practice, practice. I'm just going to be showing you a couple of examples, and at the end I'll have some practice questions that you can do. So the first case, sickle cell anemia, which is an autosomal recessive condition affecting the blood cells, occurs in 1 of every 400 African American births. You may already know that African Americans have got a higher susceptibility to sickle cell anemia because it's a selection advantage against malaria in Africa. And the question is, what is the frequency of carriers of the sickle cell gene in this population? So pause the video, have a go at it, see how well you can do, and replay when you're ready. Okay, so welcome back. So as we've said already, the information that we have is that sickle cell occurs in 1 in 400. That means 1 in 400 people of this population have the sickle cell disease. This means that the homozygous recessive frequency is 1 over 400. And if we go back to this equation, we said that the homozygous dominant recessive frequencies is represented by Q squared. So this means our Q squared is 1 over 400 because that is the frequency of the homozygous recessive genotype. And what do we want? What did the question actually ask? It wanted the frequency of carriers. So what's the carriers? Again, going back to our original equation, the 2pq was the heterozygous, okay? That was the frequency of heterozygotes, which is our carrier state. So we know we're after 2pq. So the calculation that will actually happen, these are the two equations that we're dealing with. We've got Q squared, we know what Q squared was, that was 1 over 400. All you have to do is just rearrange that by itself. So you could take the square root of 1 over 400, that gives you 0.05. And then you can use this equation up here to then rearrange the P and the Q to find P, which will give you 0.95. Just to note, a lot of people that I've met, when they do Hardy-Weinberg, they see the Q squared, they found what Q squared was, they try and put that into this equation here. You don't need to. You know what Q squared is. Q squared in this case is 1 over 400, so you can just rearrange Q there and then. Okay, so don't fall into that trap. So we've got P and we've got Q. Now we want to find 2pq. So all you're going to do is 2 times P times Q. So that's 2 times 0.95 times 0.05, and that is 0.0095. And normally we like to express this properly, so we say 95 of every 1,000 African Americans carry the sickle cell gene. Okay, so I've just times that by 1,000. It would probably be not so proper to say 9.5 of every 100 African Americans, so we want to get a whole number, so I just times by 1,000. Moving on to our next case. So albinism is a rare autosomal recessive condition characterized by a lack of melanin in the skin and the hair. The frequency of the allele in the population is 0.02. What is the frequency of the disease and the frequency of the carriers? Again, pause the video and have a go. And welcome back. So hopefully you were able to solve that. It's a slightly different question because this time we're given the frequency of the allele, not the frequency of the disease. So the information we have is the allelic frequency. And if you go back to the P plus Q equals 1, the Q was the frequency of the allele of the recessive allele. So therefore, in this circumstance, when we're dealing with an autosomal recessive disease, the allelic frequency would be Q. So Q equals 0.02. And what do we want? Well, it asks for the frequency of the disease, which we know is Q squared, going back to the P squared plus 2pq plus Q squared equals 1. And we also want the frequency of carriers, which is the 2 times P times Q. So the calculation that we do, the frequency of the disease, Q squared, we already know Q, so we're just going to square it. So 0.02 squared equals 1 divided by 2500. And then the frequency of carriers is our 2 times P times Q. So that's 2 times the 0.02, the P, times a Q. We don't know what Q is. But remember the P plus Q equals 1 equation. We rearrange for Q and then we bung it in that calculation, and that gives us 0.0392. So you can see how you can use these equations to get from one to the other or from the other to the other. So just one final thought to end on. This is more for maybe medical students, but this is for X-linked recessive traits. In X-linked recessive traits, the frequency of disease in men is equal to the frequency of the recessive allele because men only have one X chromosome. So if you have calculated or worked out a Q squared, i.e. the frequency of the disease, this would be the same as the frequency to the recessive allele. Okay, so if you found Q squared, you can just treat it the same as a Q. And here are some practice questions, just so you can get in the habit of it. I would obviously make sure you find more questions and do as many as you can, but these are some questions that I've provided for. If you just pause the video here and you can complete them, and these are the answers to those questions. All right, thank you very much for watching, and if you have any other questions on Hardy-Weinberg, put them in the comments section and I should be able to answer them for you. Thank you very much.